Hey, hello there.
Okay. Sorry, I'm late. Do you have any questions? All right, all good. So let's continue where we left off last time. From where we left off last time. So last time, right? Basically, we were discussing the system of first order equations. And roughly speaking, all right, it's going to be something like dy1 over dt is some function, right, of y1 up to yn, right, and t. dy2 over dt is some other function, right? Of course, and then dyn over dt is some function yn and t. Now, what we focus on, right, is some special cases, the special case, right, when this system can be solved for analytical solution. And the only case that worth our attention is the case where, right, it's called the partially decoupled system, right, partially decoupled. Where basically, let's say if you go from top down, it doesn't have to, it can be bottom up, right, or somewhere in between. But basically, the first one only depends on y1 and t, right? The second one depends on, right, y1, y2, and t, right? And third one depends on y1, y2, y3, and t, and so on and so forth. All right. So, well, of course, right, this is too kind of too specific and too special. So by the way, right, with that discussion, we finish chapter 2 and we move on to chapter 3, where we specialize in, right, a not a partially decoupled system, but basically, right, there's something called the linear system, right, of first order equations, ODEs, right, with constant coefficients. Okay, and it is exactly this kind of system that we'll focus on and learn how to solve for the analytical solutions, all right, of the system. So first of all, right, so 3.1, basically kind of introduction to linear systems. And I think linear algebra, right, is a prerequisite for the class. Chapter 3 is exactly where you start seeing, right, heavy dose of linear algebra being used, because a lot of concepts from linear algebra will show up in chapter 3. Okay, I will mention them and kind of, remind you of them, right, as we go along, but do expect to, use them on a daily basis and when we work on this chapter. Okay. So first of all, right, what's a linear system? Roughly speaking, a linear system is like what you saw on the quiz. Okay, maybe say right, with constant coefficients. All right. So also let me say this. So when I wrote this, right, the idea of a system of first order equations don't have any kind of limit on how many equations you're posing, right, and how many functions you're solving for. So that's why right here n is like the size of the system. In this class, we'll focus on n equals to 2, right? That's what the book does. Now, I don't like n equals to 2 only, so I'll say n equals to 3 as well. The reason is a lot of things, a lot of linear algebra, you don't see so much when n equals to 2 because the math tends to wash out a lot, like it becomes very simple. Of course, n equals to 2 is like nice, easy thing for us to demonstrate, okay, our ideas. But like to see the use of linear algebra tools, n equals to 3, right, is where we kind of start to see the non-trivial examples. And so, right, expect to be able to work, okay, on a 2x2 matrix and 3x3 matrix in general. That's the max size that will go in this class, okay? I mean, the other sizes like 4 and above, theoretically, you can handle them, right? The calculation is just going to become more complex, but I won't give them to you on the exam, for example. So what's a linear system with constant coefficient? All right. So basically, let's say if you want to pose them with n equals to 2, right? So you got dy1, right, over dt and dy2 over dt. Okay. And basically, it's a linear combination of the function. So let's call a11 y1 plus a12 y2. This is going to be a21 y1 plus a22 y2. Let me add something more. Plus, right, let's call this f1 of t plus f2 of t. All right. So for n equals to 2, this is the most general description of a linear system with constant coefficients. So where, of course, right, a11, right, a12, a21, a22 are constants. Okay, and so these are what we refer to as the constant coefficients of the system. All right, so what about these guys, right? What about these guys? These guys are viewed as like the external force, okay? Like the right-hand side, if you will. So the f1 and f2, right? When f1, these two functions, when they're equal to 0, we refer to a system as homogeneous, okay? And when they're non-zero, right, meaning they're some other function of t, then the system is non-homogeneous. I think chapter 3, or at least the first big part of chapter 3, we start to focus on homogeneous system first, okay? We'll learn how to deal with homogeneous system and then move on to non-homogeneous system later on, all right? And by the way, right, you should observe that the scheme of treating, right, the system is very, very much the same as how we look at 1.8, right? You know, you have something like ay prime plus by, right, is equal to a function of t. First, you look at, right, the homogeneous solution, where you look at ay prime plus by is equal to 0. And then, right, you look at a particular solution, so on and so forth. So obviously, right, here, the homogeneous solution is simple because it falls back into whatever technique we discussed before. So we just like, homogeneous solution, move on, right? But here, right, the system, right, this system by itself, not including these two guys, are complex enough, right? Because it's not partially decoupled, right? Y1, Y2 shows up everywhere. So we want to learn how to solve this properly first before we, include the non-homogeneous driving force. Okay, so that's why like we'll spend like at least the first big part of chapter 3 to deal with this. All right. Any questions so far? So now, right, in terms of matrix notation, okay, matrix notation. By the way, right, just so you know, not that it's super important because we don't deal with that so much. I mean, if these guys are not constants, but function of t, all right, like cosine t, sine t, t whatever, this is still a linear system, all right, it's still linear. But of course, right, the coefficients are no longer constants. And the treatment there is much more complicated, okay? So again, right, very similar to 1.8 versus 1.9. 1.9, right, allows these guys to be non-constants. But the approach there, right, was not like a homogeneous solution kind of approach, but we use the integrating factor, okay? So here, right, when these guys are functions of t, the system becomes much more complicated, and I don't think we present how to solve it in this class at all. So anyway, so the matrix notation, right, will be like this. If we're lazy, we'll just write like this: dy over dt, right? Y as a vector is a matrix A times y plus a vector f, like that. Okay, so this covers actually any size, right? So where you say y of t, this notation means, right, just means it's a vector of size n. Okay, A, right, is a matrix. So A is a matrix, so it maps vector in Rn into a vector in Rn, so n by n, okay? So A is a square matrix. F, again, right, is in Rn as well. So f of t, y of t is in Rn, okay? So that's the matrix notation, where, of course, right, A, in the above, you see is A11, A12, A21, A22. All right. And so maybe this is like the macroscopic point of view, and this is the microscopic point of view, right? You look at each entry, things like that. The point of linear algebra is you kind of, right, do both. You zoom in and you zoom out, right? Depends on the purpose of the treatment. When we want to look at some kind of macro point of view, then this is much more convenient to look at and to deal with. When you want to zoom in and want to solve for these guys specifically, then you want the microscopic point of view, for example. Okay. So, question? All right. So now let me specify, right? Let's focus on n equals to 2, and let's say, right, this is equal to 0. So in other words, I'm looking at homogeneous system, right, of a 2 by 2, of size 2. Okay, what can I say about this? All right. So now y of t, okay, is a times y. Okay. Sorry, dy dt. I'm sorry, dy dt is a times y. Okay. A times y of t, if you will. So first, right, I want to just briefly touch on equilibrium. Solutions. Okay. So again, what is equilibrium solution? Equilibrium solutions are solutions where if you start there, you stay there. Okay, if you start there, you stay there, you don't move. So obviously, equilibrium solutions are the solutions where, right, the derivative, right, is going to be zero, right, for any t, right? Of course, that what that means is that in this particular structure, that means a times y is equal to zero. Okay, so the equilibrium solutions are the solutions to the system a times y is equal to zero. Let me demonstrate, right? For example, suppose you have y1 prime, y2 prime is equal to, I don't know, 1, 0, minus 1, 1, right? Times y, right? Times y1, y2, right? So the equilibrium solutions or the equilibrium point, right, are the solutions where this is equal to 0, 0, right? Exactly like what we talked about before anyway. Now here, right, you can easily see that a times y is equal to 0 always have, right, y is equal to 0 as a solution. Okay. So what does that mean? What that means is, right, the origin, right, the origin is always an equilibrium point. Right, for the linear non-homogeneous system. All right. So the question though, right, is there any other? Okay, is there any other? Oh, by the way, right, for example, I mean, this should be quite obvious, right? I mean, think of like the spring mass system that we looked at, right, from the spring mass system that we looked at from like the previous section. If the only force, right, is playing that affecting on the spring is the spring force, then of course if you start at the balance, right, at the equilibrium point, then the mass is going to move anywhere, right? To make the mass start moving, you must move it right away from equilibrium so that, right, it starts to move, right? It starts to have a solution. But if you start at the 0, 0, and you don't give it any initial velocity, right, then it should be staying there, right? I mean, that's Newton's second law anyway, right? That's Newton's first law, right? Anyway. But the question, of course, right, is there any other? Okay. So just to give you an example, right? For example, a pendulum, right? A pendulum swing could be, right? Say it can swing on both ways, right? Could be modeled, right? The XY coordinate, right? The XY coordinate of the pendulum, right? As time goes on, can be modeled, right? As a differential equation. We won't go in there, but you can imagine that it's going to be a differential equation where the only force acting on this, right, is the I think the string, right, the tension, and then the gravitational force. Now, obviously, right, if you let the pendulum start at this position, then it's equilibrium. But there is another, right, equilibrium solution, which is the one on top, right, like that. This is a very, very, right, unstable equilibrium. So if you have to be exactly right there, right, and not move anywhere, right, then that's the equilibrium. But at least in the pendulum example, you have two solutions, right, two equilibrium solutions, right? So in general, when you have a system like this, you wonder, right, is there any other? Uh, Yeah. So that's why I say, right? The origin is always for the, oh, what am I saying? I apologize. For the linear homogeneous, I'm sorry. Of course, if it's non-homogeneous, then the force will drive it away. I'm so sorry. I mean, it's always a linear equilibrium for the homogeneous system. Sorry, not what I said before was incorrect. Because if you have the force will pull you away from equilibrium. Yeah, sorry. I mean homogeneous. All right, sorry. Yeah. Um, so, but the question is there any other, right? Is there any other, like the case of the pendulum? Okay. So, for example, looking at this, you see that, right? The only solution is 0, 0. Why? Because y1 must be equal to 0. And then plug in y1 equal to 0, you got y2 equal to 0. Okay. And so, right, this question is actually a very easy question to answer. You can look at the system by itself. But this question, right, this question can be, right, translated to a linear algebra question of, right, when does the system A times Y equal to 0 have a non-zero solution? Or in some, in some situation, you call it a non-trivial solution. Okay. When does the system have a non-zero solution? Okay. Well, do you know? Not that, it's super important here, but this kind of small facts, right, will start to be with us for the rest of the chapter and the rest of the class in some way. So linear algebra, review is in full force. When does a homogeneous system, right, have a non-trivial solution? Correct. That's very good. That's one way. Can you say some other way that's equivalent to what you say? So the following are equivalents. That's unclear. What do you mean by it's a linear combination? I think you're referring to what Adrian was saying anyway, I believe. But say a linear combination. Yes, determinant A equal to 0 is another fact. That's very good. That's true. So one, right? A y equal to 0 has a non-zero solution. Oh, by the way, right? Is always assume that A is square here, right? That will not deviate, right? Whatever size A is a square matrix, all right? 2, A has dependent columns or rows, doesn't matter. Okay, the rows or the columns of A's are linearly dependent. So linearly, right? We will review this if you don't remember. 3, determinant of A is equal to 0. Anything else? A is not invertible. Or A is singular. I mean, I guess not invertible is a more popular choice of word. 5, A does not have full rank. 5 is not used so often, but it's the same thing as this actually. 6, A has an eigenvalue equal to 0. I think the 6 should be all there is. I mean, that I know of, that worth mentioning. The rest may be some, reimplementation of these things. All right. Now let me tell you, this, and this will be featured quite often in the class. This and this not so much, but the notion of linearly independent and no linearly dependent is useful to know here. And in fact, we'll mention that quite often in class as well. Okay. So let's see. All right. What can I say? I'm not here to prove this, even though, right, the idea of the connections are not that hard. We'll hit on these topics, these concepts as we go along. But let's look at one example, okay? Let's look at the example that we looked at before. A is 1, 0, 1, minus 1, I believe, right? Minus 1, 1, doesn't matter. Okay. So it seems like, right, 1, 0, right? 0 is the only solution, the only homogeneous solution. Right? 2, what are the columns, right? This and this are independent, or this and this are independent. What do we mean when two vectors are independent? 3, this is why I say, right, with 2 by 2 is quite simple. When is two vectors independent? When are two vectors independent? Yeah, but here it's going to be much simpler than that. When you have 2, what does that mean? Yeah, one is not multiple of the other. That's it. Exactly. They are not parallel. They're not parallel. And you can see why they're not parallel, because the 0, right? The 0 will not allow you to multiply to any other ones. So 2, right? So rows and columns are non-parallel. Again, right? I emphasize what I'm saying here is only true for the 2 by 2, right? In 3 by 3 is a little more complex. But I hope you know what I mean by not parallel, right? Parallel in the sense of Calc 3. 3, what's the determinant of A? Right, determinant of 2 by 2, everyone must know, is this, right? Multiply like this. So determinant of A is, let me write down for you, right? 1 times 1 minus 0 times minus 1, which is 1, right? Non-zero. 4, A is invertible, right? Here A is invertible because 0 is the only. So we're saying exactly the opposite of all this, right? Because we have exactly the opposite. A is invertible. What is A inverse? Not sure how often we'll pull the inverse in this class. I think we might.
We should multiply that matrix with the identity matrix.
Yeah, we should. The 2 by 2 has a much easier formulation. Okay, that is A is A, B, C, D. Determinant of A is AD minus BC. Then A inverse, right? If it's non-zero, this is if, right? Then A inverse is 1 over determinant divided by dA minus C minus B. Okay. So here you can see that you can write down A inverse pretty easily for this case. A is 1, 0 minus 1, 1. A inverse is 1, 1, 1, 0. All right. So A is invertible. A has 4 rank because the rank here is 2, right? This is almost reduced. So A has 4 rank. Right. What are the eigenvalues here? We'll review the eigenvalues really quickly, later on too, because we'll talk about it. Well, trust me on this for now. The eigenvalues are 1 and 1. The reason is A is upper triangular, sorry, lower triangular. Triangular matrix, you can read off diagonals. You can read off the eigenvalues from the diagonals. What does full rank mean? If you remember in linear algebra, you did the Gaussian elimination. The number of non-zero rows or columns are called the rank, all right, or the number of pivots. So here is in the reduced form already, if you will. So this is not REF, but REF, reduced echelon form. So you have two non-zero rows, so rank is 2. So full rank means 4, like the rank is equal to the max it can be, which is 2 here. All right. So yeah. Question? Any other question? Yeah. So an example, right, where this will be violated will be something like 1, 1, 2, 2. Or, you know, we'll talk about that soon. Yeah. Or, you know, 1, 2, 2, 4, or 0, 0, 1, 2. Any of these will violate, okay, what we say above. And I'll let you, check that out, figure out why. It's clearly that these two rows are dependent. These two rows are dependent. This has a 0 rows, so that automatically makes it not vertible, okay? So you can check if you want that very quickly, right? These are the ones that will allow you to have non-zero solutions. Okay, so that the book mentioned it, not of super serious consequence, but again, it's a nice review of algebra, linear algebra, and kind of highlights, right, the concept of equilibrium solutions clause. All right. No. I mean, again, Lauren, the point of this class is to solve ODEs. So I mentioned the whole list because, like I said, linear algebra will become your companion, okay, from now on in the class, because we'll just deal with system constantly. And I think that a good knowledge of algebra will carry you through, right? A lot of these things more easily than, not a fluency on linear algebra, because there are things that we pull out of our pockets, on like day-to-day basis, like something like this. So I just list out the list as things that, quickly shift through my mind when I see something like this. You don't have to do it all the time, right? You only have to do enough to solve the solution. But like I said, right, the more you know, the easier for you to kind of make the connections. Okay. Any other question? So the second one, right? The second one that we want to mention is something called the linearity principle. We kind of allude to this, all right, in the one-dimensional case. Now we'll make it rigorous. So if you look at a system y prime, right, is equal to ay. So homogeneous, right? Dimension unlimited, meaning I don't have to do a restriction. Then if, right, y1, y2 are solutions, then c1, y1 plus c2, y2 are solutions for any any scalar c1, c2. Okay, that's a linearity principle, or someone call it's a superimposition principle, whatever. Basically you keep adding solutions as long as the system is linear. is still a solution. Okay. So why so? You can check real quick, right? C1y1 plus C2y2, right? Prime, right? Differentiate is C1y1 prime plus C2y2 prime. I hope that's not strange, right? This is like Cal 3 where you pass the derivative inside, and then, right, C is a constant, so the derivative only hits on the function of t, right? So y1, y2 are function of t, right? I just don't write down explicitly. Okay, but what's y1 prime? Y1, y2 are solutions, so they must satisfy this. So that means they are C1ay1 plus C2ay2. Well, then, factorization, right, gives us a times C1y1 plus C2y2. And reading it right from the first to the last step tells us that this is indeed a solution. Okay. Question? On the other hand, right, I mean, just caution. So if you have this, all right, the linearity principle does not, right, apply to non-homogeneous system. Okay, that is right. If you have y prime equals to ay plus f, right? Then you see that if you add, right, if you add like this, right, C1y1 prime, sorry, C1y1 plus C2y2 prime, right? You can check that it will be, right, a C1y1 plus C2y2. But what you end up adding is C1 plus C2 times f. Okay. So obviously then, right, this is not the same as this system because this is C1 plus C2 times f and not 1 times f, unless C1 plus C2 equals to 1. Otherwise, right, in general, that's not true. So, right, the f here, the non-homogeneity, right, is basically, it's just saying, right, the behind the linearity principle is the mundane fact that 0 plus 0 is equal to 0, right? But if you have non-zero, right, then non-zero plus non-zero is 2 or something. So that's why. Okay. So I think the textbook gives you some example where they say something like this, and I think it's worth looking at. Y2 prime, and they say y1 prime is equal to 1. Y2 prime is y1 plus y2. And they say linear principle does not apply. You can check by just solving it out, things like that. I'm not gonna work it out for you. I think it's a little bit of a cute example, because if you just superficially glance at this, you might think that this is a system with constant coefficients. Okay. Yes, it is, but it's not. It's a non-homogeneous system. It's not a homogeneous system, because if you want a homogeneous system, this guy must be multiplied with y1 or y2 or something like that. The one by itself, right, looks innocent, but actually it's a driving force. It's the f, and that's why linearity principle does not apply to it. Simply by that, if you know it's a non-homogeneous system, it's out. Okay, it's not that mysterious. The only thing that might be mysterious is you might be confusing, and you might be confused. You might think that this is a homogeneous system. It's not. Okay, that's all. Any question? Okay, so now maybe this is time to review linear independence, okay, and dependence. So it's this. It's a very general fact, okay, so I'll just write it like this. A collection of vector y1, y2, let's say up to yp, okay? And let's say these are all in Rn. Again, right, I'll just spell it out for you. These are n-dimensional vector, right? Are linearly independent. Okay, let me say this. Linearly dependent, I think it's quicker to pose it this way. If there are C1, C2, up to CP, right? Not all zeros, so that C1y1 plus C2y2 plus CNYN, sorry, CPYP, right? P here does not have to be equal to N, is equal to 0. Okay? So if you can do this, they are linearly dependent. Actually, it's very intuitive, right? What this definition is. Basically, just think of the opposite. They say not all zeros, right? What happens if they're all zeros? If you choose they all to be zeros here, then obviously, right, this must be 0 on the right-hand side. So that's a trivial way to make them 0. On the other hand, if you have a non-trivial way to combine them to make them to be 0, then that means they will depend on each other somehow. Okay. So I guess alternatively, okay, because not all of them are zeros, right? Not all of them are zeros. Not all of them are zeros. That means that there is some C, right? There is, right, some, let's say some CI is non-zero, right? It's not 0, so you can divide. So that yi, okay? Because of this, right? Yi is going to be 1 over Ci times minus C1y1 minus C2y2, right? You skip the I, right? Ci minus 1, yi minus 1, Ci plus 1, yi plus 1, Cpyp. Okay. I think you may appreciate this more, because basically what it says is, right, the ith vector, some I vector, can be written as a, oh, by the way, right, this is called a linear combination, right, linear combo. Linear combination of the other vectors. So in other words, this is not super needed as far as the span, right, of the vectors is concerned, because you can always replace whatever the action of this guy by the action of the remaining guys. Oh, I'm so sorry. I mean, all of them are negative. I'm just so caught up in the moment. They're all negative, sorry. They're all negative because basically you subtract them over on this side and divide by the Ci. You isolate the yi, right? Yeah, sorry, typo, yeah. Okay. So yeah, right, any of these are, right, equivalent facts to say they're independent. And they are independent, right? They are independent. They're independent if they're not, right, dependent. That's simple. Okay. So that's it. Now, let me pose to you one more thing. This expression is not as isolated as it looks. This expression, right, can be written as y1, y2, yp as a matrix times c1, cp is equal to 0. This right here is an n by p matrix. Okay. So in fact, right, linear independence and dependence are very much connected to homogeneous solution of a system. So actually, it's just another way to phrase this. And you ask why the columns are independent, that kind of thing. It's because exactly it fits in right there. All right. So you can say, right, exactly that a set are dependent if the matrix formed by the columns, right, well, formed by the vectors, only have, so the matrix is dependent if the matrix formed by the vectors as columns have non-trivial solutions for, homogeneous system, and is independent, right, if the matrix formed, right, as columns, by columns as a vectors only has trivial solution. All right, same way. So for example, right, you see, I claim, right, that these guys are all dependent because, I say that they violate whatever above. Check, right? For example, if you look at the rows, right, it's clear that 1, 1 minus 2 times 1, 1 plus 2, 2, right, is equal to 0, right? So that's a linear combination, right, that gets to 0. So that's dependent. If you look at the columns, right, it's even easier. Minus 1, 2 plus 1, 2 is equal to 0, right? So dependent. Same game here, right? Here, actually quite easy. Every time you have a 0 vector, then you're already dependent. Why? You just play by itself. For example, 0, 0, right, plus 0 times 1, 2 is equal to 0. Or you're like, what you're doing, right? You make it a 0 here. Sure, but the requirement is, right, not all the C's are 0. So because I have a 0 vector here, I can choose a coefficient to be 1 here. So that's already good. So this is also dependent, right? Okay. Any question? Okay, so you see the connection very soon to the ODE, okay? So right now, one more fact. Nope, eigenvalue will come later, Saga. Right here has nothing to do with eigenvalue yet. So one more fact, right? If P is bigger than N, all right, so if you have a collection of vectors of n-dimensional, where you have more vectors than the dimension, then they are guaranteed to be dependent. Right? In other words, the biggest independent set you can get in an n-dimensional context, right, is a set of size n. And actually, that's called a basis, right? That's called a basis for the vector space of Rn. Anyway, so let's see how this connects back to what we looked at, right, from the linearity principle. So the linearity principle says okay, that if you have a y prime, right, equals to ay, then c1y1, right, plus c2y2 is a solution if y1, y2, right, are solutions. So let's say that A, right, is a 2 by 2, let's say. Then what this observation tells you is this, that first of all, right, that you just need to find y1, right? You need to find y1, right, and y2 as two solutions that are independent. All right. I will clarify this a little bit, all right? There's some subtle issue here. The reason is these are function of time. So how do you classify a vector, right, as a function of time, okay, as independent? But I'll tell you later. But basically, roughly is similar to what we said before. But the point is this, that after you found that, right, then linear combination of them is a solution. And the observation above, that you cannot find a third one, or you do not need to find a third one, because any third one, right, will be dependent on the first two, okay, because the dimension is 2. So in other words, after you find 2 solutions, that's it, because of what we said above. So then if you, after you found 2 solutions are independent, then all solutions will be y of t to be c1y1 plus c2y2. Okay. So that's the generic principle that we use to find all homogeneous solutions for our system. Basically, if it's an n by n system, you find n independent solutions, and then you do a linear combination, then that will cover all possible solutions that you will find, okay, that you need to find for the system. No more, okay? Actually, maybe the interesting question is why no less, all right? Why no less? Like why can you get away with one solution only, for example? I think I have to go back on that. But basically, if the A is not, I think if the A is not degenerate, then you always have at least two, you must go with 2 solutions. I think that's a thing. So what I tell you here is, right, you cannot have more than 2 solutions if a system is 2 by 2, 2 independent solutions. You cannot have more than 3 independent solutions if it's 3 by 3. All right. Why no less? Let me think about it a little bit, and I'll tell you maybe next time. Okay. It has to do with the we don't pose an A in a trivial way to begin with. So sure, I mean, like trivial solutions, right? Trivial solutions in this case will be 0, 0. Y of t is equal to 0, 0. The equilibrium solution. But guess what? Exactly like I said above, the moment you throw in 0, 0, you automatically make it a dependent system. So actually, right, it violates what I said here, that you must make them independent. So yes, right, you pointed out explicitly, but implicitly what I said here, exclude, right, 0, 0 chosen as a solution, right, to construct all solutions. Yeah. Okay. Any question? Okay. So yeah, next what I want to tell you, right? Yeah, okay. I have a easy answer for that, but I haven't shown you why. It's basically because all these matrices must have at least 2 eigenvectors, and each eigenvector give you a solution, and it has to have 2 eigenvalues, that kind of stuff. It's future material, right? For now, I don't have an easy way to tell you. So basically, Ron, it's not that simple. I thought of that, but basically because the matrix A, right? When you think about it, the matrix A can map it into some subspace, for example, with 1 dimension, right? So let's say when A is degenerate, when A is like 1, 1, 2, 2. But in this case, you still have 2 solutions. So something there that I'm not kind of seeing, right? So I think it's not about by the basis only. Yeah. I don't know how to explain it abstractly for now. But when you see how we solve for, eigenvalues, eigenvectors, you see that it always have these many solutions. Yeah. Okay. So what I want to tell you is, this. What do we mean by independent solutions? All right. Because notice, right, there's something that I'm hiding behind saying this. The reason is when I define this, all right, this is for static, okay? This is for static vector, meaning vector not a function of time, okay? Because these are basically just numbers, and I say I'll do this combination. On the other hand, right, y1, y2 are vectors, but they are not static vectors, right? As time change, their value change. So what do I mean by they are independent? Two things you can do. First is you can say they are independent no matter what t is. That's correct, okay? So in other words, when I say y1, right, y2, right, as function of t, right, as a vector function of t, are independent, okay? What I mean is they are independent for any t. Okay. So of course, right, when you fix a t, then they become static. So you just do what I did before. So basically what I say here, if it's 2 by 2, then what it's saying is like, this guy is never a multiple of that guy, okay? For any t. But what is a remarkable fact, okay, is this. Remarkably, if, okay, this is big, y1, y2 are two solutions to y prime equals to ay, okay, and y1 t naught, y2 t naught are independent for some t naught. Then y1 of t, y2 of t are independent for any t. Okay. So it's remarkable because the meaning of this statement is this, that once independent, always independent. Like this independent property propagates through time. Of course, what's the cost? The cost is they must be the solution to the same system, right? They must have some tying each other together somehow. Otherwise, of course, you can always construct two things where, they start out independent, but they somehow become dependent, right, in some later time. But it's remarkable because as long as they are solutions to the same system, then, right, once independent, always independent. That's remarkable, okay? And the proof of this, if you're interested, I'm not going to talk about this, but if you are interested in seeing it, is problem 35, section 3.1. Okay, it's quite good. I don't know, Daniel. I don't know. I think they are kind of different. Okay, uniqueness is about a calculus result where solutions don't cross. Solution curve do not cross. Independence is an algebra result where you say that these two solutions, right? These are each is a one single dimension, right, of the solutions, they never really become parallel to each other. I don't know if that's a byproduct of uniqueness. I don't think so. Yeah, it's different. Again, take a look at this, all right? And you see, basically the proof is not that hard, but it also introduces you to something called the Wronskian, which is something I think you've seen somewhere before, Jacobian, that kind of stuff. It is quite nice. I mean, if you want to take a look, all right. I'm not going to go into it, but I'll just talk about implication of this for us, okay? The implication of this for us is this, that, when you deal with this system, right, most of the time in practice, you need to deal with initial condition, okay? You need to deal with initial condition. So you need to deal with y prime equals to ay, okay? And let's say y of 0, right, is given as some vector, okay? Now let's say you found, okay, you found y1, right, y2, okay? So that at time 0, they are independent. Okay. First of all, right, then y1t, right, y2t will always be independent. That's guaranteed by what I just said. But also, right, you will always be able to solve for the initial condition. Doesn't matter what the initial condition is. We will also always be able to solve for the initial condition. No matter what it is. No matter what this value is. Okay, why so? And what do we mean by this? Right? Like, like your quiz, right? You solve for the initial condition, you solve for C1, C2. Same thing here, right? Because, right, first of all, the linearity principle says that the general solution will be this. Right? To solve for the initial condition, you need to decide what C1 and C2 are. Okay? What do? You plug in 0, right? You plug in 0. So if you plug in 0, right, you got C1, y1 of 0 plus C2, y2 of 0 is equal to the y0. Okay, as the initial condition. Now, how in the world that I know that C1, C2 will always exist? Several things you can do. By the way, right, so here, I guess this is a 2x2 system, all right? Otherwise, what I say won't be true. But it's a 2x2 system, okay? So what you can do is you can rewrite this as a matrix. Okay, where C1, C2 is to be solved. So in fact, right, what I'm saying is this, and you will see this more when you do system. Solving for initial condition is like solving a linear algebra exercise where you have to solve a system of equation, unless it's nice, so things simplify a lot for you. So this right here will be a 2x2 matrix. Okay, a 2x2 matrix. Now, this is where facts 1 to 6 will be useful again. Why? Fact 1 to 6 says that if these two columns are independent, right, that's by assumption. These two columns are independent. So this matrix is invertible. But if this matrix is invertible, right, let's call this matrix whatever, y or something, y of 0 as a matrix, then C1, C2 will just be the inverse of that matrix times this. So that's why you can always solve for C1, C2. You can always solve for C1, C2, right? No matter what the initial condition is, as long as you have independent solutions, okay? But that also highlights, right, the peril. If you are not careful and you're not solving for independent solutions, then in some way, right, going back to, I think Ron mentioned the word basis. This is where basis actually is used, because this is saying that y1, y2 form a basis of the plane R2, all right? If y1, y2 form the basis of the plane R2, then any vector can be reached by the basis. That's what it says here as well. But if you're not careful to not form a basis with your solution, then, right, you will not be able to reach a certain point on the plane. Okay, that means you cannot solve for the initial condition. That means somehow your solution is not correct, something like that. Or you have non-existence at that point or something. All right. So that's kind of like the implication of independence, with how our solutions are constructed, how we solve for the the initial condition, that kind of thing. It's a little bit of an abstract treatment, all right. I admit. I can't give you a non-trivial example here, because that will ask me to solve for these solutions. And like, can I? I think last time we did something, but you see example of this later. All right, that's what I mean, because like we'll talk about how to solve this. But this lecture, right, is all I want to do is I want to kind of bring out the concept of linear algebra, okay, and show you how it's connected to the way, okay, that we structure the solutions to ODE. No, you see, no. So let me give you a very trivial example, right? So suppose, okay, suppose that, let's say, let me see. So y1 prime is equal to y2, and y2 prime is equal to minus y1. So 0, 1, minus 1, 0, I think, okay? So, okay, I'll demonstrate to you so you see what my notation means. This is the inverse of big Y, not small y, okay? Like this. So first of all, I claim that, right, one solution is cosine, one solution is sine. So how do I write this? So y1, okay? So the solution y1 of t is, hold on, give me a moment. I'm not sure if this is true. Let's just pretend that this is the solution, okay? Yeah, I know. So let's just suppose that this is the solution, okay? Like this. Cosine t and 0 sine. No, that's bad. That's bad. Hold on. Sorry. The reason it's bad is I'm just giving you a bad example. Hold on. Here. Give me a moment. Let me try again. Yeah, suppose y1 of t, all right, is, let's say, 1, 1 e to 2t. y2 of t, okay, is, let's say, 2 minus 1 e to minus t. Okay, no, it's fine. I want to demonstrate to you. I just kind of like want to see what context I want to demonstrate in. All right, so I don't want to give you a system. I just want to demonstrate the idea of solving for the initial condition. Okay, so here I claim that, first of all, right, y1 of t, y1 of 0 is independent of y2 of 0. Okay, how? Well, y1 of 0, right, is going to be 1, 1. And y2 of 0 is 2 minus 1. Okay, so they're independent. That's what I want to say, first of all. Second, right, let's suppose you have an initial solution. Let's say y of 0, right, let's say is equal to 1, 1. This is the initial condition. Okay. Then my general solution is y of t, right, is a combination of y1, y2. So it will be C1 times 2, sorry, 1, 1, e to 2t plus C2, 2 minus 1, e to minus t. Okay, that's the general solution. Now, if I plug in 0, I'll get C1, 1, 1, plus C2, 2 minus 1, right? And that's supposed to be 1 and 1. Actually, I think this is too easy, right? Let me change it to 1 and 2. Okay. So first of all, right, I claim that the left-hand side is the same as, right, if you want to do it slow, is C1 plus 2C2, C1 minus C2 is equal to 1, 2. But this is also equal to 1, 2, 1 minus 1 times C1, C2 to be 1, 2. This right here is what I call big Y of 0. This is what I call little y. So my apology, right? I shouldn't call this a vector. It's a matrix. It's just a matrix y of 0. So no vector notation, sorry. Right, this is what I call y of 0. This matrix. And this is what I call little y of 0, which is the initial condition. Okay. And what I say is this, because these two vectors are independent, this matrix is always invertible. And so your C1, C2, I can solve for it, but abstractly it's also equal to the inverse of this times 1, 2. That's what I mean. Is this okay? No eigenvalue for you today, Sagar. I think we will get it next time. Yeah, it's multiplying. All right, it's multiplying. So again, I mean, like there are many notations, right? When we start to do this kind of stuff. So yeah, feel free to clarify with me. All right, where my notation means something, and I'll be happy to give examples. Okay, to if I could to demonstrate. So the idea I want to say here is only, right, that with independent solutions, okay, with independent solutions, you can always construct, right, independent matrix at the beginning to solve for the initial condition. But of course, right, let me show you this. Suppose that, suppose somehow that you propose that y1 is 1, 1 e to a t, and y2 is 2, 2 e to minus t. Then if you do this, if you experience, you know that something is wrong right away, okay? If you experience. Why? Because if you look at y1 of 0, is not independent with so in other words, these are not two proper solutions. You make a mistake somewhere down the road where you construct something like this, okay? So I know that. But also a consequence of this is you will not be able to solve for all initial condition. Why? Right? So of course, this is wrong, okay? The structure of our solution will not allow you to solve for this to begin with, to get down to this to begin with, as you will see. But second, like another way you can see it is not possible, okay, to solve for all conditions. So let's see. Suppose I let my initial condition be, let's say, again, 1 and 2. Okay. Then what does it say here, right? C1, right? Y1 at 0 plus C2, Y2 at 0 must be 1 and 2, right? But that would be C1 times 1, 1 plus C2 times 2, 2 to be 1 and 2. You see clearly this is impossible because here, right, the left-hand side, the top and the first and second rows are equal. Here, the first and second row are not equal. So it's impossible, all right? So of course, right, it comes from the fact that these solutions are wrong to begin with. So again, right, I'm kind of giving you some what to expect in the future. But in the future, right, your proper solutions will look like something like this, where it's independent vectors, right, multiplying with some exponential of some factor. And exactly these are the eigenvalues that you will learn in the second section. Okay. Any other question? Okay, so we'll continue next time. But one more thing I want to say is this, that again, notations are very, very, and it starts to get heavy here, all right? So pay attention. So when I use capital letters, okay, I almost always mean matrix, okay? Capital letters means matrix. Arrow means vector, okay? That's why I was admitting that I use a confusing notation. This is supposed to be a matrix, so there should not be an arrow on it. But one more place where I recognize that I could have confused you is this place. Let me see here, where I write down something like this. Sorry. Yeah, I also write something like this, okay? And I call it y1, y2 as well. Unrust. So here, when I write something like this, okay? What I mean is this is a row. This is a scalar, all right? This is a scalar y1. A scalar y1. So this y1 is different from the y1 vector that I wrote, okay? That's why I recognize that I might be confusing you when I write this. So when I write this, this means it's a row, the first row of the solution. This is the second row of the solution. When I write this is the first column of the solution. This is the second column of the solution. Okay. So for example, right, I mean, just clarifying notation here. For example, when I do this, okay, this is vector y1 as I wrote. This is vector y2, okay? But if you want the scalar y1, then the scalar y1 will be c1 eta 2t plus c2, sorry, yeah, 2c2 eta minus t. The scalar y2 will be c1 eta 2t minus c2 eta minus t. Yeah, I do. All right. So is that okay? I want you to not confuse my notations with the vector notation and the scalar row notation. All right. I mean, if you confused what I say here, you may get the wrong idea of what I'm talking about. Are we okay? You see what I get this y1 and y2 from? Okay, good. Yeah, just want to make sure. All right. So I will be very careful with my notation. All right. So if somehow what I say doesn't seem to make sense, or vector doesn't seem to be a vector, whatever, ask me. All right. I will clarify what object I'm talking about, because scalar vector matrix should be always distinguished. Okay. So if there's no question, we'll continue on Thursday. All right. Yeah. Thank you. You have a good one too.